So we've seen the world is full of complex dynamical systems. And complex dynamical systems are full of surprises. There's self-organization happening, but self-organization does not necessarily produce beneficial or desirable outcomes. Congestion, most people would think, is not what we want. Crowd disaster is not what we want. Financial crashes is not what we want. So how can we make sure it's going to produce something good? And this is where the Internet of Things comes in and can help. It's now possible to cheaply measure a lot of data about all sorts of things with little sensors connected to the Internet. And I'd like to claim that with the Internet of Things, we can now make self-organization work 300 years after Adam Smith's invisible hand concept. He had formulated it, he had assumed it would have always beneficial outcomes. So invisible hand is just another word, I would say, for self-organization. But we know that not always is the outcome desirable, and the question is how to reach that. We also know from complex dynamical systems that the outcome depends on the interactions. And so choosing the interactions or changing the interactions could change an undesirable outcome into a desirable one. And that brings us to the discipline of mechanism design. In many cases, people use agent-based modeling and simulation in order to try how little changes in the interactions would change the collective outcome of the self-organization. And this can actually be used. It works. And I'd like to show you a simulation that starts by simulating the unwanted stop-and-go flow that we've seen before in the experiment. Now I show that simple models can reproduce that dynamics. Of course, you all know that. This is, by the way, the coffee meter. Don't try it now. And of course, nobody wants to have this. So we'll now take the helicopter in order to see what the damned reason is for that congestion. And it turns out, oh, there is an on-ramp. And there are some vehicles that are squeezing themselves into that traffic flow that produces small perturbations in the flow that will be causing domino effect and amplification effect and eventually a stop-and-go flow. But we'll now turn a driver assistance system. I mean, we let cars accelerate and decelerate automatically. Like autonomous driving using, say, laser sensors or radar sensors or whatever you have, and video sensors. So we change a little bit the interaction, and as you can see, the traffic congestion dissolves, even though we have still the same inflow. It's gone. And there's no control center that controls all that vehicles. This is distributed self-organization. And the only thing it takes is basically real-time measurement and real-time feedback that changes the acceleration, deceleration behavior a little bit. There are some papers about that, of course, that go into detail. I don't need to convince you that increasingly we have smart vehicles that have something reminding of perception and communication, perhaps cognition, perhaps even, or decision making. All of that can be built now with measurements and with algorithms or even AI. And we've done that also quite a few years ago, before people were talking about Google self-driving cars even. We were working with car company in Europe. The car on the right is actually the one using our system. The car in the back is the one that was using the system of that car company at the time. And they liked our system quite a lot because it was better handling changes in the variation of speed of the lead car. And what did we do? We basically used a model of driving behavior, in that case the intelligent driver model, and variants of it. It just contains very few parameters. Most of you probably know that model even. And the idea was that we could change parameters of the driving style depending on the traffic situation. In free traffic, we would not interfere. We would just reproduce the natural driving behavior of the driver. Then there's approaching the upstream end of congestion. There's driving in congested traffic, driving in the bottleneck section, and downstream of the congestion. And now, importantly, how do we dissolve traffic congestion? By reducing the time gap between cars. When they go very slow, so that increases capacity, but at the same time it happens to destabilize the flow. So in order to compensate for that, we have them accelerate more quickly. And the combination of the two things manages to increase capacity and have reasonable stability. So here we have a driver assistance system that actually offers traffic assistance, not just comfort for the driver. It creates a collective effect in the sense that it dissolves traffic jams. And even if not every car is equipped with that technology, like if there's 20 to 30% of cars equipped and all the others just do what they always do, it would still work. I think this is pretty amazing, and it shows the power of using self-organization to solve problems. Now, back to game theory. I mentioned the Brace paradox, and in connection with the Brace paradox, people often speak of the price of anarchy. So if you let people independently decide, in brackets selfishly decide, or rationally decide, basically more or less equivalent terms, then the collective outcome will often not be optimal. And so what can we do about that? Now we can punish people by charging them a price, a congestion charge, or road pricing. We can control the cars. So if they were all autonomous cars, they would probably be connected to some control center too. And however, there's a different approach, and perhaps a much cheaper one. It's not taking away all the freedoms. Actually, the price of anarchy is not that big in most cities. It's just a few roads that mess up the system. And it's actually possible to identify those roads. There's some famous example, when they closed down 42nd Street in Manhattan. At that time, I think some people were surprised that this was improving traffic flow in Manhattan. Perhaps we shouldn't be so surprised because it was a diagonal road cutting through a square grid of roads. It was just disturbing the regularity. And now they have a pedestrian zone partly. It's really nice, and everyone is happy with that close down of 42nd Street. Now, what about Delft or Amsterdam? I can't tell you really, but we've done it for Barcelona. Barcelona, like many other cities right now, is thinking about getting green and sustainable, and what could they do. And there's a lot of talking about closing down roads. There's a super block model among other models that are discussed. And so what have you done? Javier is our PhD student who's done that really excellent work. He's created a digital twin of Barcelona. Took a lot of effort. He had also empirical and mobility data in order to calibrate everything. And so we are reasonably trustful of the meaning that this digital twin is meaningful, that it can tell us something about what would happen if we did this or that. And so basically what we have looked into is different ways of closing down roads. As you can see over here, it could be many roads closed down or less roads closed down. And it's not intuitively clear what would be the best solution, which is different from the 42nd Street, which we could have guessed. So we have to do a lot of computer simulation. Javier has done that, and he has looked into the performance, and there is some variability in performance because there's also some randomness in the computer simulation of the traffic flow. And you can see over here that actually there are some solutions that are improving the environmental situation quite a lot, kind of minimizes CO2 emissions, while at the same time highly performing in terms of avoiding congestion. So we're closing down roads, but in a smart way. And it turns out a minimally invasive approach is actually best. It's not like if we close down many roads, that will be the best for the environment. It could be horrible even in terms of congestion. We just need to figure out which are those road segments that basically disturb the harmony in the system and the harmony with nature, in a sense, And that can be done with massive computer simulations. In this way, we can identify solutions. As I said, it's not the solutions that have massive changes that are best, but solutions that have a few targeted interventions. And then price of anarchy is largely gone, so we don't need to worry about it anymore. Totally unexpected solution, perhaps. We don't have to force people then to take this route or that route, so we don't have to charge them. It's just, just close down a few roads and know which ones to close down, problem solved. Of course, there are companies who like to sell expensive congestion charging technology and so on, but the question is what implications does it have for our society, for democracy, for freedom, and all of these kind of things. So that should be considered as well, I believe. There's another thing where self-organization can surprisingly help to improve the situation and get rid of a lot of congestion. And it's congestion that produces a lot of CO2 emissions. So, of course, all the cities want to get rid of congestion, but often this is what you see. This is what you get. I went back when I was in Cairo for a holiday. I recorded this intersection over here, and I really love it because it's self-organizing so nicely. And there's so diverse traffic participants, cars, buses, lorries, pedestrians, cyclists, horses, donkeys, camels. And now I think a perfect example for diversity. And it works so nicely. We have unidirectional flow in the front. That's one of the components why it works. We have unidirectional flow in the back. And importantly, we have a little buffer in between, which allows everyone to adjust the speed in such a way that you will find a gap in the flow to cross when you need a gap. So adaptability. This is designed for adaptability, and therefore for self-organization. Now, you don't hear the noise. There's a lot of honking. And we don't want that. But with Internet of Things, we could do the same thing, like let self-organization happen silently. And the question is, how would we have to do that? At least that was inspiring our approach. We were looking for an adaptive traffic light control for complex street networks, for that can handle with traffic disruptions like building sites and accidents, and also can handle particular events such as Olympic Games, pop concerts, and so on. Okay, and we were quite, I was young at that time, you know, we thought it just reinvent traffic light control. Let's start from scratch. I should say it was one of the most complicated projects we've ever looked into. And we faced limitations of our imagination, but we found very interesting results. And it was inspired by those self-organized oscillatory flows. Remember this, there's a bottleneck and the pedestrians show these oscillatory flows. There's no traffic light here, there's no police, there's no law, no control. It just happens as self-organization. Then we saw, couldn't we have that also at intersections? Aren't intersections also bottlenecks, just more complicated ones? Couldn't we have a pressure principle that produces those self-organized oscillations, produce oscillatory flows at intersections? Couldn't we have traffic flows control the traffic lights rather than the other way around? And couldn't we have a bottom-up control rather than a top-down control? And what would be the implications? And then we just did it. And you can see over here that for a Manhattan grid, or also, you basically have very nice self-organized green waves. And how does it work? In simple terms, we measure the outflow of cars from road sections, but we also measure the inflows. And based on the inflows, we make a very short-term prediction or anticipation of how many cars would be there in the vehicle queue, and how much green time would we need in order to dissolve that vehicle queue fully, if possible. So cars would not be unnecessarily stopped. But try to minimize the number of stops of cars in a sense. Okay, and now we were comparing 3 different approaches. The left one is centralized traffic control, the traffic control center. The traffic control center tries to get as much data as possible and then act like a benevolent dictator, try to come up with the best possible control and impose it on the city in a top-down way. Then this is what is totally decentralized. Each intersection would independently minimize travel times based on the inflows from the neighboring road sections. It doesn't care about what happens far away. There's no coordination between different intersections. It's a little bit like in economics, Homo economicus, every intersection selfishly does the best possible job at that location. No coordination, though. So you'd think this should be better because it coordinates different intersections. That should be worse. And that should be the worst even, because what we do over here is we do interrupt the travel time minimization sometimes to clear long vehicle queues in order to avoid spillover effects. But this is just friendly to our neighboring intersections. You know, why should that intersection care about that? Okay, intuitive, that should be best, second best, third best. And the reality is just the other way around. Red line is for top-down traffic control. Increasing capacity utilization produces longer queues, as expected. But surprisingly, to some extent, the self-organization, self-control approach would produce much smaller queue lengths. And this is understandable for very low traffic volumes, because then you can give every single car a green light when it arrives. That's the adaptiveness. Okay. However, then over here it totally fails, right? Suddenly the queue lengths explode, and we can't even enter this area of capacity utilization. So the traffic control center would say, see, and that's why you pay a few millions every year, so we make sure we can still operate in this area. Interestingly enough, however, the third approach, the other regarding one that cares about the neighbors and produces a little bit of coordination, a coordination that spreads through the system, however, that produces better solutions all the way. So far, this is all based on computer simulations, simplified scenarios, kind of almost theoretical in a sense, you know? But then we were brave enough to go to the traffic control center in Dresden and said, you know, we want to do a project with you together. And they said, well, we are happy with the system we have. We just bought a new traffic light control, the best on the market. It produces green waves, even adaptable green waves, you know. But there's one thing we are not happy with. You see, a pretty irregular road network even, yeah? With a lot of different buses and trams cutting through this area in different ways. And they said, we want to prioritize public transportation, but we can't, because if we do that, we interrupt the green waves, and when we interrupt the green waves, we get congestion. It will be a monster congestion very quickly, and we'll not get rid of that for a long time. So if you think you're smart, you know, then come up with a solution that's better with the best system on the market. And okay, smart PhD student Stefan Lemmer tried to do this with the same empirical data that had been used to calibrate the other system. This is the system, the state-of-the-art control that they had implemented. You see those green waves over here. That's what happened with our self-control approach. Also green waves, but much less regular. Is this a good or a bad thing? We don't know yet. But here, things get pretty clear, right? We could actually prioritize public transport. We managed. But not at the cost of motorized traffic. They even had an improvement as well through this increased adaptability, which basically uses gap in the traffic flows as an opportunity. And it was also good for pedestrians and cyclists, okay? And there were all sorts of news reports about it, and said chaotic traffic control lets traffic flow better, and basic democracy for traffic. You know, how is it possible we're living in a democracy and then there's a dictatorship in a traffic organization, in a sense? And of course, that was a bit provocative, I admit that. And there was a large newspaper article that says, the revolutionary idea of the professor, traffic controls the traffic lights. And then there was a little complimentary article that said, Zurich is afraid that there would be induced traffic, more traffic, if Helbing's plan works too well. So is there a solution that works too well? You know, so at that time they didn't do it. There was even an article that said simulator basically turns our worldview upside down, like a Galilean revolution, basically, in the way we would basically manage traffic flows or societies altogether. So traffic lights control themselves. It was just too much for people at that time. And then it took again, a couple of years, many years, in fact, and another city was daring to make the experiment. It was just 30 minutes from Zurich, Lucerne. And so they were making measurements before they changed the traffic control. Of course, they also had their system before. And then our system was implemented. Actually, I was not personally involved. It was my previous PhD student who, interestingly enough, created a company together with a previous guy running the traffic control center of Zurich. So he left that control center to establish that company with my previous PhD student to implement that self-organizing traffic light control in Lucerne. Okay? I learned later on about that even when everything was done. So I could not interfere at any point. It was evaluated by another professorship, and here you can see the result. Red means cars waiting. A lot of congestion with the system that they had before. This is after they changed to self-control. Quite substantial improvements. 14% less waiting times for pedestrians, 33% less waiting time for public transport, 23% less waiting time for cars and bicycles. So then there was another newspaper article, more green for everyone. How is this possible even? Just by not wasting green time when you don't need it. You need to give green when it makes sense. So we changed the pattern in which we distributed green time. I mean, not me, but Stefan and Christian Heimgartner. They did it, but based on that idea that Stefan and I had developed and published about before. So we got rid of, at least in computer simulation, of traffic congestion on freeways. Okay, at least some of it. We got rid of quite a bit of traffic congestion in cities, at least in some places where we could do our experiments. And now the question is, can we also improve safety of pedestrian flows? And also the organization of pedestrian flows. And back to that famous Japanese crossing, I think this was a crossing where an interesting observation was made. That if you have two crossing pedestrian flows, you would have, again, another self-organization pattern. A bit similar to the lane formation, but the generalization of it, it's stripe formation. And it allows the magic thing to walk through a stream of pedestrians without stopping. If there was a single pedestrian trying to walk through that stream, it would be almost like a wall. But if there are many pedestrians, then this happens. Stripes will form, and those stripes move forward while pedestrians move sidewards within those stripes. And that allows them to move forward without stopping. And again, they don't even have to think about it. It just happens by responding to everyone else in the neighborhood. You don't have to, if I ask you in an exam, come up with a solution to this problem of two crossing flows, I'm not sure you would come up with that stripe formation thing. Analytically, it's not trivial, but we can do that just by interacting with each other, And so we can learn something from that, because we have 3 or 4 crossing flows. There is a pretty chaotic situation in the intersection. However, if we divide that intersection of 4 flows into 4 intersections of 2 flows, then we get the stripe formation in each of those intersection areas. Not here. Here it's done the wrong way. Here it's done the right way. So stripe formation in such a way that you would have a circular flow that is supported by that design. Okay? So you can design for self-organization. You can design for the support of desirable self-organization patterns. Same thing for buildings. There are corridors, there are narrowings, and there are intersections. And all of those design elements are not optimal. I would almost have said wrong, you know. This is most easy to understand. If we cut away those corners, then it will be a smoother flow. It will be like a funnel, right? But it shows us that less can be more. Less space can improve sometimes the performance of the system. And that's why those pillars here in the middle of that corridor can actually stabilize counterflows, as we see it over here. So at the moment, everyone is coming towards us, and a metro arrives, and after some seconds, actually, we'll have a subdivision of people who go this way, people who come towards us on the other side. So the pillars are stabilizing the separation of the two opposite flows. And this is what I just showed before, that it's possible, considering also that there's a preferred side of walking, to induce rotary flows that would be more efficient. Now also there are really big problems that had to be solved throughout the world and will have to be solved in the future. One of those examples is the Jamrad Bridge. So this is a central building in the context of the Holy Hajj, the Muslim pilgrimage. And there have been many crowd disasters in the past. And it was therefore decided that the design and organization had to be changed. And so the old Jamrad Bridge was replaced by a new one with multiple levels, and moreover, the organization of the flows in the plaza has been changed also completely. In particular, it was avoided that there would be kind of widenings where people would perhaps make a rest. Widenings can be as bad as bottlenecks sometimes. And a unidirectional flow was implemented. Plus, there were many other measures taken, including a scheduling approach, a flow monitoring, adaptive rerouting, and so on. And that improved the situation dramatically from what it used to be, where emergency vehicles were basically unable to pass even the crowd and reach the people in need in many cases. Towards a situation that was much more orderly, and pilgrims were a lot happier with. Also because it took less time to reach the Jamrad Bridge and get back to their tent camps. And that means if they spend less time, it will be less crowded, and that will be much more comfortable. Okay? Also, we've been looking into the Love Parade disaster in Duisburg, and we've done computer simulations, plus, as we'll see in a minute, we have also done virtual reality experiments. We have been looking into several different scenarios. As you can see over here, there are two ramps. One ramp was not used at that time, but it could, of course, be used. Then we were looking into the police cordons and what their impact was on the overall flow dynamics and outcome. And here is a table which basically shows those outcomes. We'll not go through all those numbers, but the conclusion is the police cordons were actually not improving the situation. Of course, they were trying to, but those control attempts were counterproductive. And this is really important to realize. More control is not always better. It can be deadly. And there are other things that it can do basically to assist or support self-organization. This includes providing people information about how crowded the situation is in different places and offering them alternative routes, rerouting them, all based on information feedback, basically. I'd like to end on collective intelligence. I was very short in my previous presentation. But I do think that collective intelligence has a huge potential, in particular for democracies, and I would say societies altogether. And the idea is pretty old. 1714, the fable of the bees was published. And so the idea was that we could organize society like a beehive. And it could work in a wonderful way. Now, interestingly enough, in a beehive, yes, there is a queen bee, but that queen bee does not command all the other bees. There's a lot of self-organization happening. And how do they do that? And there are a lot of biologists who are looking into this, and now there are models, computer simulations, all of that. But can we transfer that really to our society? Learn something for how to manage ourselves better. Can we upgrade democracy digitally? How to bring the best ideas of many minds together? And it turns out that diversity wins, not the best. There are many examples for that. Not just the Netflix prize, but here it was pretty obvious. They were offering $1 million to everyone who was able to improve the algorithm that the company used at that time by, I think, 10% or so. So they had a good algorithm, they wanted a better one. And then there were dozens of teams that were applying for this $1 million, and actually, I think for a long time, even more than 2 years, if I remember it right, nobody managed to get above this threshold until the best performing team started to combine their solution with solutions that were performing less well. I think, why were they doing this? Couldn't that only deteriorate their solution? But just the opposite was the case. Immediately they were jumping over that success line. They got the $1 million, and then all the other teams said, oh, let's combine our algorithm with other algorithms as well. And all of them could have done it by just combining several different approaches. So not the single best solution made it. None of them. Only the combination of solutions. I mean, diversity was needed to solve the problem. Okay. And I do think democracy is about enabling distributed knowledge and collective intelligence, and how to do that. And in fact, here we can learn from bees. What bees do is when they look for food and harvest it, they send out some bees to explore the environment. It's an independent exploration. And then eventually they come back and report. So there's a phase 2 information exchange. And they do this wiggle dance. They have a way of expressing their excitedness about the honey sources that they found. They're a little excited. Other bees will not copy that. If there is a lot excited, then other bees will go in that direction indicated. So there's information exchange, and there's integration. So basically, it's very important that there is independence in the first step, then information exchange, and then in the third phase, basically, solutions are combined. And then you might have still several combined solutions. This is when you need to vote. Now, interestingly enough, we most of the time use majority voting, and it turns out to be one of the worst methods to do voting. That's why democracy often doesn't work, I would say. There are various issues, and I'm now talking about an application example that's called participatory budgeting. So a city says, hey citizens, here is money that we give you. You can now sit together and decide what you want to do with that money. Okay, and how do you decide how to spend that money? This was kind of the issue. And participatory budgeting is quite popular in many cities. However, it still has issues. And if you apply the majority rule, what happens is typically most of the money goes to the center where there's the highest population density and more voters, and the periphery basically gets nothing. And over 20, 30, 40, 50 years, that creates social inequality and social tension and problems, and we see that in many different cities. And banlieues, for example, so there's no spatial fairness, or not enough of it, and so we need different, better voting rules. We got interested, what can we do? So basically there are several elements of voting. One is the voting input, that's basically how you express your preferences. Eventually that goes into an aggregation procedure that determines the democratic outcome. And we've built an app, a smartphone app, to make experiments with different kinds of approaches. And one of the approaches is approval voting, where basically there are different options given, and you can say, I like this, I like that, the other options I don't like. This goes into the ballot box. There's also a method called combined approval voting, and here you can do more things. You can approve, you can abstain, or you can disapprove. And that again goes into the ballot box. Furthermore, there is the so-called rank voting, where you can change the order of the options according to your preferences, priorities. And there is accumulative voting, where you have a certain number of points that you can distribute over the different options, and you can give different numbers to each option. Oh, what happened here? Bit messed up. 1 point here, 3 points here, 2 points there, 3 points there. Okay? Goes into the ballot box. Okay, so this is about different input methods. There are more even than that, and then we can also vary the output, the aggregation method. And so if you do majority voting, basically just the options that have most votes will be approved until we run out of money and everyone else gets nothing. Okay? That's the typical thing. But it totally neglects the costs of those projects. And instead what you can do is you can calculate the number of votes divided by the costs. So then you can see how popular is a project as compared to the dollars or euros or whatever you need to spend. And then you get actually a different selection of projects. Okay? And there's a further method that's called the method of equal shares. So here virtually everyone gets a certain amount of money, and they can distribute that amount of money over different projects, and those projects that accumulate enough money will be implemented, and the other projects basically not. Of course, there's some leftover money by those projects that don't make it. That's going to be redistributed again. So it's a bit a complicated approach, but this is an interesting approach also. Important point is there are different voting methods, all a form of democracy, which have very different outcomes. And what you have today is typically a situation where one or a few projects grab most of the money and there is basically no money left for everyone else. And these are disappointed. Well, it doesn't have to be this way. Take another voting method and you have the opportunity to fund a lot more projects. Okay. Now from theory to practice, we have actually done a real-life experiment in the city of Aarau, not Barcelona. Barcelona was inspiring this project, that we varied the voting rules, okay? And so with the city together, we had many meetings with the citizens. I see Josh, another PhD student, Regula. But most important are the citizens. And there was some brainstorming going on. I'm not sure. Yes. Deliberation, Mentimeter, brainstorming in order to activate collective intelligence, basically. And so people came up with a lot of ideas, more than 100 even. And those were then attached to the map of Aarau. You can see where those projects were located in the first session, and there were further sessions, and there people were partially merging their projects, and they were working them out. Some of the projects, people lost interest, or it didn't have the necessary quality, it was not feasible, whatever. So eventually there were 33 projects worked out and considered to be feasible. And then these are the projects, 32 of them at least, and then there was the voting. And we were trying to create trust through transparency. We explained how the voting method would work, and that it would also be important that not only the number of votes, but also the costs. And that created a situation that made all the proposers of project cost conscious. We had cost-efficient project as a result, and then there was this final countdown. The 10 points were distributed of all the voters, and those are the projects that were finally funded. And you can see that overall, those are the projects that got particularly many votes as compared to the cost. I'm about to finish, yeah? Yeah. Okay, now let's see what the outcome was. 17 projects were funded. All the different districts of the city got some money. This would have been the situation if majority voting would have been applied. 7 projects would only have been funded, and all of them in the center of the city. That means proportional fairness, which we applied over here, was creating also spatial fairness, a lot more of it. Also, we figured out that the approach was a lot more inclusive because there were more younger people who participated in the voting than in most other referenda. More elderly people, more women, more foreigners. So it was really in every dimension, it was more inclusive. People saw the opportunity to make a change to the better. So I'm concluding with this slide, saying that democracy can be upgraded. We can have more projects approved, we can have more resourcefulness, which is important for sustainability. More participation, more inclusion, more transparency, more trust, more satisfaction, and more fairness. And I would say that's better than optimal, because optimization just tries to maximize a one-dimensional goal function. And a one-dimensional goal function will never be good enough to represent the diversity of needs and interests in a society. But voting doesn't care whether everyone agrees on a goal function. You could have different goal functions. We can still vote. And the outcome could make many of us a lot happier than what we have today. Thank you so much. That's it.